Welcome back, everyone. Today we are talking about the slope-deflection equations and how we can use them to solve for indeterminate beams. Let's begin with a quick derivation of what the slope-deflection equations mean. Now, the slope-deflection equations will give me the end moments, Mn and Mf, and end forces, Rn and Rf, of any beam as a function of the loading along that beam, and the end displacements and rotations. Now, we'll be using the subscript n whenever we talk about the near node or the beginning of the beam, and we'll use subscript f for the far node or for the end of the beam. Now, to derive this, we look at each of the components individually. So, for example, I have a rotation here and a rotation here. I have displacements, and I also have the load. So let's start off with a discussion of the rotation at the near node. So if we have rotation at the near node and we're ignoring everything else, we would have a deflected shape that looks something like this. And that is representing a beam with a pin on one end and a fixed end at the other. And we could have some moment applied here. And it's causing a rotation theta n at my near node. Now I can use something like the force method to solve for my reaction forces and for this applied moment. And if we do that, we'll find that this applied moment is equal to 4EI over L times the rotation. And the opposite moment is going to be equal to 2EI over L times that rotation. And then the two forces are going to be equal and opposite. On one side, it's 6EI over L squared times the rotation, acting up. And on the opposite end, it's 6EI over L squared times the rotation, acting down. Now I can do the same thing for rotation at the far node. So if we draw that displaced shape, it looks something like this. And you'll notice I'm going to make that rotation counterclockwise. For this method, we'll always assume that everything counterclockwise is positive. So this rotation here is theta f. And in order to apply that, I need to have some kind of moment at this end. And the deflected shape is going to match something of a fixed end on one side and a pin at the other. So if we find all these moments and reactions, we'll find that this one is 4EI over L times the rotation theta f. On the opposite end, 2EI over L times theta f. And then my forces, once again, are 6EI over L squared times the rotation. And in the opposite direction, 6EI over L squared times the rotation. So now I've got rotation at both ends. Let's now add in displacement. And I'm going to do both displacements at once because all that matters is the difference in displacement between the two sides. So let's say we lift up the near node by some distance un, and the far node gets lifted by some distance uf. And this looks effectively like two fixed ends, but they're being lifted relative to one another. And once again, I can solve for all my reactions for this system. So if we do that, my moments are 6EI over L squared times the difference in displacement. So that's un minus uf. And on the opposite end, it's the same moment. So it's 6EI over L squared times un minus uf. And then my forces are also going to be equal and opposite. So this is 12EI over L cubed times the difference between the displacements. And likewise, 12EI over L cubed multiplied by those difference of the displacements. So now I've considered motion of both sides. I have displacement, I have rotation. Lastly, I need to consider my load. Now, the load is going to be applied as though it's on a fixed beam. And we do that because we've already encountered motion of both sides. So we already have the case where we have rotation and displacement at the near node, and we have rotation and displacement at the far node. So if we're going to combine all these together, we don't want to double count that rotation or displacement. So we'll apply this load as though it's acting on fixed ends. We can calculate the reactions for this. So there's going to be two moments and two forces, and we call these reactions the fixed end forces and fixed end moments. So FEF stands for a fixed end force. And we have one at the near node and the far node. And then we have fixed end moments, FEM, at the near node and at the far node. Now, these fixed end forces and fixed end moments, they are tabulated for a lot of different load considerations. I have a few of them down in the description below, but you can also search online for a wide variety of different load cases. But these fixed end moments and fixed end forces, they represent the loading on your structure. So now that we've considered all of our effects, we have rotations, we have displacements, and we have our loading, we can combine all these together with superposition. So if we do that, we end up with the slope deflection equations. And these equations represent rotations, displacements, and my forcing to give me my end moments, Mn and Mf, and my end forces, Rn and Rf. Using these equations is going to flip our paradigm in structural analysis on its head in some ways. Previously, we've looked at finding the reactions and shear and moment diagrams directly, particularly for determinate systems. With the slope deflection equations, our primary unknowns are going to be the displacements and rotations throughout my beam. So what we'll do is we'll find all the displacements and rotations first, and then we will use those in the slope deflection equations to find a variety of reaction forces and reaction moments. So let's see how that works in action. For our first example problem, let's consider this 3-span beam. 2 of the spans are loaded with 3 kips per foot, and they're all equal spans of 20 foot each. Now, as I had mentioned, our primary unknown is going to be unknown displacements and rotations. So in this case, at my fixed ends, I know I have 0 rotation, 0 displacement. So those are known quantities. I also know I have 0 displacement at my 2 rollers. However, my 2 unknowns are going to be a rotation at B and a rotation at C. Now, if I can find those 2 rotations, that means I can find my moments and forces in all 3 of these segments. So let's do that. To begin, we'll split our beam up into its components. So I have a beam for AB, and then here's the connection between A and B, and then a beam BC and CD, also with the connection between those 2 as well. And we know our unknown is going to be the rotation here at B and the rotation here at C. So in order to find those, we need some equations in order to solve for those 2 unknowns. So the first equation that we're going to look at is the sum of moments at this location B has to be equal to 0, and that corresponds to rotation at B. And then we'll have another equation corresponding to our unknown rotation at C, which is the sum of moments at C is equal to 0. So now let's look at what those moments are at B and C. At B, we can have a moment here, and we'll call this MBA. That's the far moment on AB. And we'll have another moment here, MBC, which is the near moment on segment BC. Likewise, at location C, we'll have 2 moments there. This is MCB, which is a far moment, and MCD, which is a near moment for CD. So therefore, taking all those things together, we see that MBA plus MBC is equal to 0 in order to satisfy equilibrium there. And also MCB plus MCD also has to equal 0. So that gives me 2 equations, 1, 2, for my 2 unknowns, theta B and theta C. So let's write out all 4 of those moments using the slope deflection equations. Let's start with moment BA. That moment is the far moment of segment AB, and that equation is EI over L multiplied by 2 times the rotation of A plus 4 times the rotation at B plus 6 over L times that difference in displacements. So that's UA minus UB. And then I'm going to add on my fixed end moment for BA. Now we can see that point A is a fixed end, so it has no rotation, it has no displacement. Point B is resting on a roller, so it also has no displacement. The fixed end moment for a distributed load at this far end is a negative 1/12 WL squared. Reason it's negative is because that moment is acting clockwise, but MBA here is acting counterclockwise. And so therefore, if I substitute that in, I have 1/12 times 3 is W, times 20 squared for the length, and this is equal to negative 100 kip feet. So taking a length of 20, we'll find that this equation is EI over 5 times the rotation at B minus 100. Now we can repeat this for my remaining 3 moments. So we'll look at moment BC. This is a near moment of BC. So we'll have 4 times the rotation at B plus 2 times the rotation at C plus 6 over L times UB minus UC plus the fixed end moment BC. Fixed end moment is going to be positive 100 in this case. I have the same load, 3 kips per foot. My length is 20, except that moment is acting counterclockwise, so it's going to be a positive 100. I can see that my displacements cancel out because both points B and C are supported by rollers. And therefore, I'm left with an EI over 5 times the rotation at B plus EI over 10 times the rotation at C plus 100 for that moment BC. Next, let's do moment CB, and it's another far end moment. So this is going to be 2 times rotation B plus 4 times rotation C plus 6 over L times the difference in displacements plus the fixed end moment at CB. And to no surprise, we'll find that this is EI over 10 times the rotation B plus EI over 5 times rotation at C minus 100. Lastly, let's look at MCD, my final moment. It's a near moment for CD. So we'll use the near moment equation. It's a 4 times rotation at C plus 2 times rotation at D plus 6 over L times the displacements. So that's UC minus UD plus the fixed end moment for CD. Now for this span, we'll notice that point D is fixed, so it has no rotation, has no displacement. Point C is a roller, and there's no load along the span at all, so therefore there's no fixed end moment either. So taking that all together, this is EI over 5 times the rotation at C. So now let's plug all of these moments back into our equations for the sum of moments at B and the sum of moments at C. For my first equation, I need to take these two moments and add them together, and the sum of that is going to be equal to 0. So if we combine those, that's 2EI over 5 times the rotation at B plus EI over 10 times the rotation at C, and that's all equal to 0. We notice that we have a minus 100 and plus 100 that cancels out there. For equation 2, we're going to add up our 2 remaining moments here and set that equal to 0. So if we do that, we'll find that this is EI over 10 times the rotation at B plus 2EI over 5 times rotation at C minus 100 is equal to 0. So now I have 2 equations. I have 2 unknowns, which is theta B and theta C. So I can solve for those 2. And theta B is going to be negative 66.67 divided by EI. And theta C is a positive 266.67 divided by EI. Now we'll take those 2 rotations that I just found, and we'll use that to find all of my moments and all of my forces. So here's a summary of what we know so far. My near and far rotations and displacements are already listed here for the boundary conditions, and all my fixed end terms are also located here. We can substitute in our rotations that we found. So these 2 right here are rotation at C. That would be the far rotation for AB and the near rotation for BC. And I also solved for rotation at C, which is the far rotation for BC, and the near one for CD. Next, we can substitute those all into the slope deflection equations, and I strongly encourage using a spreadsheet for this. It's very tedious, but it is not too challenging. So once we do that, we'll find all of our moments and forces for AB, BC, and CD. Now, if we want to look at our reactions, let's say we want to look at the moment at A, that's just the near moment for AB. So that reaction moment is 93.33 hip feet. And if I want to look at my reaction at A, that is just the near force located at A. So that is equal to 29 kips. Now for the reaction at B, you actually have 2 components coming in there because you have a force here on AB and a force here on BC. So that's going to combine the far reaction from AB and the near reaction from BC. So 31 plus 33 is equal to 64 kips. And the same thing is going to happen with my reaction at C. It's going to be 27 plus 4. So that's equal to 31 kips. And lastly, if I look at point D, my reaction moment and force is just whatever's happening at that far end. And so MD is 26.67 kip feet. And RD is equal to a -4 kips. Now the signs in this case are moments are always counterclockwise positive. So both of these end moments are counterclockwise, and reaction forces are positive up as we've drawn them for the derivation of the slope deflection equations. So I have one downward reaction and the remaining are upward. So now that we've seen one example, let's talk a little bit about some special cases where the slope deflection equations can get simplified down. So the first case that we'll look at is what happens if we have zero moment at one of these sides. So let's say, for example, Mn is equal to 0. Well, that sets this equation equal to 0. And I would like to solve this equation for the rotation at the near node. And I can take that expression and then I can substitute it back into these other three equations. And I can rewrite those slope deflection equations for the case of one end moment being equal to 0. So if we do that, we'll see we now have just three equations left, and we've gotten rid of one of our unknowns. So now we only have one rotation to deal with, and it's the rotation where we still have a moment. So the rotation where a moment is 0 has effectively been canceled out. Now this was for the near moment, Mn is equal to 0. You can do the same thing for the far moment if that's equal to 0, and the equation looks awfully similar. It's just that you now have the rotation here for theta n. And be careful with your fixed end moment terms. All three of these are the fixed end moment at the near node, and these three are the fixed end moment at the far node. So let's do a quick application of what that looks like. Let's have a very similar beam, except I've taken away my fixed ends. Location D is actually a cantilever, and it has a 10 kip force acting down. Now, if I look at all my unknowns, I'm going to have an unknown rotation here at A, unknown rotation at B, unknown rotation at C, and at D, I both have an unknown rotation and an unknown displacement. So it looks like I have 5 unknowns in this case. Let's see how we can handle that without solving a system of 5 equations. So let's start again by breaking this up into its components. So I have 3 segments of beam from AB, BC, and CD. And I'm going to start with this cantilever end. And I'll show you the second shortcut that we can use when we have cantilever ends. The cantilever end is rather special because you know you have 0 moment and force here at the end. So therefore, you can just solve for this force using the sum of forces in the y direction. So therefore, that has to be 10 kips up. And you'll also have a moment at this location for your internal moment just by taking a sum of moments. And so that moment, we'll call that MCD. In this case, is equal to 200 kip feet. So therefore, for cantilever ends for CD, you don't need slope deflection equations at all. Just solve for your moment and force directly. Now, if I look at AB, AB is going to have 0 moment at this location at A because that's the end of my beam and it's a pin. So therefore, I'm going to use the simplified 3EI equations for this. And then for my segment in the middle, I have to use the normal slope deflection equations because it is in general going to have moments at both ends. So once again, if we look at our unknowns, I have an unknown rotation here and here. And so I'm going to look at my sum of moments at those locations. So once again, I'll have an MBA plus MBC is equal to 0, and also an MCB plus MCD is also equal to 0. So those are going to be the 2 equations that I'll have to solve. We'll note that I don't actually need to solve for my rotation at A because there's no moment at A. And I also won't need to solve for my rotation and displacement at D because we don't need slope deflection equations for cantilevers. So here, let's do a moment MBA. And since I have no near moment there, I'm going to use the expression for 3EI divided by L, multiplied by the rotation at B, plus 1 over L times displacement A minus displacement B. And the fixed end moment term gets a little bit more complicated, so it's plus fixed end moment BA, and then minus 1/2 the fixed end moment from AB. So we can see that displacements are 0 at both ends, so I don't need to worry about those. And then calculating this out, this is going to be 3EI over 20 times rotation B minus 100, which is the fixed end moment at BA. That's negative 1/12 WL squared for distributed load. And then I have another minus, and this fixed end moment is going to be a positive 100. So we'll have a minus positive 100 divided by 2. Now for moments BC and CB, the two moments acting on my center beam right here, those are the same as what we did in the first example. So we'll just quick copy those right here. And then we'll move on to solving our equations of equilibrium. So starting with our first equation, we're taking the sum of moments at location B. So that's taking this moment plus this moment and setting that equal to 0. So if we do that, this equation is 7EI over 20 times rotation at B plus EI over 10 times rotation at C minus 50 is equal to 0. And for my second equation, I need to take the sum of moments at C, so that's this moment that I calculated here, and MCD is just 200 kip feet. So adding those two together, I'll find that this is EI over 10 times rotation at B plus EI over 5 times rotation at C, and then I'll have a minus 100 here plus 200, so that ends up with a positive 200 is equal to 0. So once again, I can solve my two equations for my two unknowns, and I'll find that my rotation at B is 333.33 divided by EI, and then my rotation at C is equal to a negative 666.67 divided by EI. And I'm going to take those two rotations and substitute them back into my slope deflection equations to find all my forces and moments. So once again, let's start with a summary of what we know and what we do not know. So we do know our displacements here at all of our boundary conditions, and the fixed end terms, we know all of those. We don't actually need those fixed end terms for CD because we already have the moments and the forces for that cantilever without using slope deflection. Next, we can put in all of the solved displacements and rotations. So you'll notice I don't know my rotation here at A, nor do I know my rotation at D or displacement at D. But it turns out I don't need any of those quantities. For CD, I've already found all my forces and moments just using equilibrium on the cantilever. And for AB, for these remaining three terms here, I'm going to use my shortcut slope deflection equations where one of those end moments was equal to 0. So if we go ahead and we apply all those equations, we'll find that we have our end moments and end forces for each of those cases. And so I can find my reactions. Reaction at A is just the near force at AB, and so that's just 25 kips. Reaction at B is a combination of the far force at AB and the near force at BC. So 35 plus 25 is equal to 60 kips. And lastly, I have an RC. My reaction at C is going to be the summation of the far force for BC and the near force for CD, which is going to be a total of 45 kips. And that wraps up how we can use slope deflection equations to solve for the reactions of indeterminate beams. So as always, I hope you learned something. Please subscribe. I will see you next time.